Alright, this will show you how to graph the data for the candle burning lab. I set up a few things already for you. For example, I put volume down here and burn time over here. Depending on when in the year we do this lab, you'll either know or not know exactly where to put what variable and where. So the way it always works is your independent variable, that's this variable here, always goes on the bottom of a graph. The dependent variable, that's the average you calculated over here for burn time, always goes on the y-axis for a graph. Probably should have written average burn time here. First thing we need to do is come up with a scale of numbers to put down here and a scale of numbers to put over here. The rule is that you have to take up more than half of the graph and you have to start at 0. So what we'll do is we'll start at 0. We'll look at our averages here. Now your data might be different than mine, but I'm going to use the ones I have. So the volumes range from 50 up to about almost 1200 here. It turns out if I count by 50s or skip a line and count by hundreds, that scale will work pretty good for me. 300, 400, 500. Okay, to save time in the tutorial here, I'm just going to write the first digit, 600, 700, oops, 800, 900, 1,000. I'll go ahead and write the 1,000. This is going to be 1,100. And then if you went past 1,200 in your data, that's going to put a spot out here, which technically you're not supposed to do. You may have to redo your scale. You could, instead of counting by hundreds, for example, you could go every other line a 75, and I bet that would work for you. So that would be an option. Okay. Now we need a scale for our y-axis, and I need to graph all the way from 3 up to about 73. So what I'm going to do is, again, you start at 0. Okay. And I think skipping a line and counting by tens just might get me there. And again, you have to take up more than half of the graph, and I think that's going to do it. And I could number all the way up there, but that's enough for the data I have, so I'll just stop. And then it's just like math. You're going to graph your x, that's your x, and this would be like comma y. So 56 comma 3. So I'm going to go to 56. Here's 50 right here, so 56 comma 3. I'm going to have a data point just about there. Okay. And then I'm going to have to go 113 comma 7. 113 is close to 100, comma 7 is going to be about right here. And then 264 comma 18. 264 comma 18. Now I got this data from a student, okay, so it may or not be perfectly accurate, but it'll give you an idea how to graph it. 200, 300, 264 comma 18. 410 comma 27. 410 comma 27. Let's see, that says 708 comma 44. And the last one here is 1,118 comma 73. 1,118 comma 73. Now I can tell by looking at this data, because I've done the lab for so long, that there are some errors in the data, but it's not bad. And so now what you do is you draw a line of best fit. That's not a dot to dot. So do not just connect your dots like this. That's not what you do in science. Instead, you average your data points, because that will account for any errors. And what you're doing is you're kind of trying to draw a line here that will average them out and I think that about does it. So basically what I'm saying here is you'll see I have a data point here that's a little high. This one's a little high, but that one's a little low. So they're averaging out. So and this one's a little low. So what you're saying is if you recollected data without any errors, you actually think the data points should fall on that line. And so you draw a nice, smooth, perfectly straight line through that data. Okay, now, you never actually collected data for an exact 1,000 milliliter beaker. So what we want to do is we want to use that. On yours, I think you have a spot to make a prediction. Tell me what you think a 1,000 milliliter beaker would burn for. The actual one you had was more than 1,000. So we can use our data to do that. So what you do is you go to your 1,000 line on here. I'll use a different color here. You draw a dotted line straight up. You should probably use a ruler for that. Till you hit right here. And then if you read across the graph over this way, and you can draw these dotted lines on your actual graph, it'll tell you what a 1,000 milliliter beaker should burn for. And I'm getting approximately 67 seconds. Right? Now we can use that data to figure out how long the fish tank will burn for. Okay? So 67 seconds is what I predict for a 1,000 milliliter beaker, even though I never actually measured the 1,000. I measured ones bigger and smaller, but I can use my best fit line, my graph, to figure that out by going up and over and reading this number. And that's what I get. This is what I get for my graph. So we just figured out that a 1,000 milliliter beaker, if we draw a dotted line up and over on our graph, we can figure out how long a 1,000 milliliter beaker would allow a candle to burn. And in the data I collected for the lab, I got 67 seconds. Yours might be different. Okay, so I'm going to use my data to show you how to solve this problem. And what is the problem? The question is, how long would the candle burn in a fish tank, if you remember that from the first day. So before we get there, though, a couple side notes. First of all, 1,000 milliliters is actually the same thing as a liter. So just as a reference point for you. So a 1 liter beaker would burn for 67 seconds in my case. So let's go back to the fish tank. You put a candle in here. You burn the candle till it goes out in the fish tank, but you actually didn't get to do this. You have to figure it out without actually doing it. So we can actually use the data we just collected here to figure out how long it would burn in that fish tank. And that's what we're going to do right now. So, first of all, I think I have a typo here on my screen. This should be 31, not 25. Okay. So, we could fill the fish tank with water like we did before, dump out tons of water and figure out the volume of the fish tank. But there's a much easier way. It's a rectangle shape, and most of you remember from a math class you've had in the past that you can measure length times width times height to get a volume. So that's exactly what I did. I measured in centimeters, 49 times 31 times 25, and I got 37.975 centimeters cubed. Now, if we divide that by 1,000, we'll figure out how many liters that is. Since we're dealing with liters over here, we want this to also be in liters. And that turns out to be 38 liters. So the fish tank I had in class is 38 liters. Now, we can set up a simple cross multiplication problem to figure out how long the candle would burn in here. So we know that a 1 liter candle would burn for 67 seconds. Okay. Now, if we cross multiply, we take 67 times 38 and 1 times x, we will get an answer over here in seconds, and that would be I'm working on it, sorry. That would be 2,546 seconds. And if we wanted to figure that out in minutes, we would just divide by 60. So if I divide that by 60, I get 42 minutes. Now, that actually seems pretty high to me, but that was the data I had gathered from a student to do the tutorial with you. So using my data, I would predict that the candle would burn for that long in the fish tank. So use your data to see what you have, keep track of your work here, and in your conclusion you're going to have to explain how you did that using the numbers you have. Thank you.